Hello, everyone. Can people tell me if you can hear me? I've got the green light here, but this morning I pulled a classic blunder. I was actually muted and talking, and it took me about a minute. So people were watching me like talk without hearing me for about a minute. But when these live streams start, if you could just like let me know if people, if you can hear me, that gives me some reassurance. I see the levels here are okay, but I just type in, can people hear me? Okay, thank you very much, Candace. All right, well, let's begin. This week, because of Monday was a holiday, it was a little bit shorter, and so we just covered one topic, which was vectors. Next week, we're going to use vectors in 2D kinematics, and then the week after that is the week of the test, and we're just going to review everything during that week leading up to the test. Okay, so vectors. I have two questions here regarding vectors. Vectors are needed for 2D or 3D or higher dimensions because to locate something in 2D, you can't do it with just one number. You need two numbers in 2D. If we were to do 3D, you'd need three numbers in 3D and so on. Okay, and so vector is basically, at least in 2D, we're just going to do 2D in this course. Vector is a pair of numbers. Okay, and they're needed for any kinematics because kinematics is about position or velocity or acceleration. Okay, so each one of those kinematic quantities would have to be expressed in 2D as a pair of numbers. And that's actually what my second problem is all about. I'm not going to actually solve it because you haven't watched the videos on 2D kinematics. That's for next week. But I'm going to kind of lead into them with my second question because the first question is just converting vectors. And you might wonder, well, why are we doing this? This just looks like plain old math. The second question kind of shows you why you need vectors because I have a situation there which is a two-dimensional kinematic problem, and I'm going to ask you for the initial position, initial velocity, and so on. And I'm going to argue that there's no way you can specify the initial position with just one number. You'll need two numbers. Okay, so question number one is what the last video was about. It's basically converting between polar and Cartesian coordinates. So vectors in 2D, you need two numbers, but how you interpret the two numbers depends on whether you're using Cartesian or whether you're using polar. And actually, there's an infinity of different possible ways you could do that. But for this course, we're just going to use Cartesian and polar. And so, you might have a point in your xy plane, and its location is specified in polar coordinates, but you want to convert that to Cartesian. How do you do that, or vice versa? Okay, so let me introduce that first with this whiteboard here, and let's imagine that we have a two-dimensional plane. So this, that white square that you're seeing there could be like a field. Maybe you're looking down on a field, and I think actually in one of your labs you're going to go out into the park, and you're going to use a compass, and I think you're just going to pace things off. You're going to locate objects in the park by just walking around in there. Okay, and so how do you do that? Well, if you go back to I guess it was my second lecture where I introduced general 1D kinematics. I had that car driving down the road, and I said, if I ask the question, where is that car? You answer it by saying, where is it with respect to some reference point, like a tree, okay? And so you put the origin at that tree, and then you say, where is that car? And you could say, well, that car is at 3 meters or 5 meters. You only need one number because that one number specifies, how far from the tree the car is. But in two dimensions, you can't do that. So again, just imagine that you're looking down at a plane here, and this is like your x-axis like that. Okay, so you're going to place an x-axis down here, and here's the y-axis. Oh, that's terrible. Let's try that again. There's your y-axis there like that. Okay. And there's a point. And I guess here that the origin, there's some reference. Like, I don't know, maybe you can imagine that that's like a tree, okay? And you say, okay, that tree is going to be my origin, and then some direction is going to be your plus x direction, and then some other direction perpendicular to that will be your plus y direction. And suppose you want to locate this point here, P, somewhere in the xy plane like that, okay? And let's do polar first. For polar, I would tell you how far away from the tree it is, okay? And that's r. All right, so there's r. It's just a measure of how far away from the tree it is, and I'll label it as r. But if all I give you is r, that's not good enough because, you know, I tell you it's say 10 meters from a tree, but is it 10 meters this way, or is it 10 meters over there, or is it 10 meters that way, or is it 10 meters that way? I mean, there's an infinity of different possible directions, and so I not only have to tell you how far it is from the tree, but I got to tell you what direction you want to walk. And the way we do that is we take the plus x-axis as a reference, and we measure an angle starting from the positive x-axis here, counterclockwise until we get to the R line there like that, okay? And that is theta. That's the angle theta like that. Now, the way you can imagine this is just imagine that, say, the plus x-axis is kind of like the hand of a clock, and the hand will turn, but it turns counterclockwise. So it starts along the x-axis and then it turns until it gets to R, and whatever angle it turns through, that is your angle theta. And I think, you know, without trying to prove this with any depth, I think intuitively you can understand that if I tell you how far you have to walk and I tell you the direction in which you have to walk, it's easy to not easy, but you'll find that point P. Okay, you'll uniquely specify that point P. Okay, this is polar. Let me switch to blue, and I'll show you how you do it in Cartesian. So here, actually, let me do it in green. Here's the point P, and if you draw this dashed line here, this is a projection down to the x-axis like that, okay? And where it crosses the x-axis, that's the value x like that. All right, so basically you just drop a perpendicular line to the x-axis. That line is perpendicular to the x-axis like that, and wherever it crosses the x-axis, that's your x component, okay? And same thing for y, you draw it over here like that towards the y-axis, and wherever it crosses the y-axis, it's y. And now if I give you x and y, I have again uniquely specified the position of the point P. So imagine you know, you're at the tree here, and I tell you walk a distance x, and you say, okay, I'm going to walk a distance x here like that along the x-axis, and then you stop, you turn 90 degrees, and you travel a distance y along the y-axis, and then you'll also wind up at the point P like that. Okay, so those are two equivalent ways of specifying where that point P is. And if I give you r and theta, you ought to be able to find x and y, and if I give you x and y, you ought to be able to find r and theta. Okay, so that's what our first problem is about. It's going to be converting r and theta to x and y, or conversely, x and y to r and theta. Okay, and well, let's start here. So the question says state the quadrant. Now you don't need that when you convert from polar to Cartesian, but you'll definitely need it the other way. But for practice, we'll do it for all of them. So state the quadrant and convert the following, obviously the other form. Okay, so let's start off with the first one. And the first one is converting from polar. Polar is r and theta, and I give you r and theta, so you're going to be converting away from polar to Cartesian. And the formulas for that are quite simple, actually. And they're like, there's no ambiguity about them at all. You just plug in and solve, or crunch them through your calculator. Okay, so here's the formula. Actually, maybe I should just, before I give you the answer, let me just show you the formulas. The formula x is equal to r cosine theta. All right, and you know everything on the right hand side because you know r. I give you r, and I give you theta, and then you can calculate x. And for y, it's y is equal to r sine theta. You know, give you theta, give you r, and you can calculate y. Okay, and there's nothing more to it than just plugging in. Okay, so for the x, plug in r is 7 like that, theta is 35 like that. Okay, and crunch it through your calculator, and you get 5.73. All right. Now, just a few things that you should be careful about here. Uh, in this course, we're going to need radians sometimes and degrees sometimes. For these problems, we're going to be working in degrees. Okay, so on your calculator, make sure that you switch to degree mode and not to radian mode. Otherwise, you'll get the wrong answer. All right, so that's the first thing. The second thing is uh, you know how to do this on your calculator, because some calculators are different. Okay, and I could show you the calculator that I have here on my computer, my virtual calculator, but it might be different than yours, and so make sure you know how to do that. Like on some of the newer calculators, all you have to do is type 7 times cosine and then 35 in that exact order, and it'll work. But on some of the older calculators, you have to punch in 35 first, then cosine, and then multiply it by 7. Okay, so if you don't know how to do that on your calculator, I can show you, but it would have to be during one of our Google Hangouts. Okay, so there's the answer. Oh, I'm looking at what's going on here. I apologize, guys. I think I'm on the wrong screen here. I was saying the right things, but it should be that one. Okay, they're similar because I was cutting and pasting, and I think when I switched over to the other window, it might have switched over here. But anyhow, it was the same material. I was just like pointing to the wrong screen. Okay. Anyhow, I have r is equal to x is equal to r cosine theta. Substitute r 7 and then 35, and then that's going to equal 5.73. Okay. And same thing for y. If you do that with the y value here, you're going to get that, like that. Okay, and so there it is. That's the first one. Okay, now I also asked for the quadrant, and for the quadrants, maybe we should just quickly switch back to the whiteboard here, and I'll show you how the quadrants work very quickly. Let me do this, I guess, in maybe purple here, like that. This is quadrant 1 over here. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Okay, so if you're talking polar, quadrant 1 is 0 to 90 degrees. Quadrant 2 is 90 degrees to 180 degrees. Quadrant 3 is 180 degrees to 270 degrees. And quadrant 4 is 270 to 360 degrees. Okay? So that's how you can determine it if you have theta, if I give you the answer in polar. Okay, if I give you Cartesian, you can still determine the quadrant, because quadrant 1, both x and y are positive. Okay, so in quadrant 1, x is positive here, and y is also positive, like that. Okay, in quadrant 2, x is negative and y is positive. In quadrant 3, they're both negative. And in quadrant 4, x is positive and y is negative. Okay, and so that's what's going on if you're with the quadrants, if you're working in Cartesian. Okay, so let's go back to our questions here, and I ask state the quadrant for that one. Okay, so that's between 0 and 90, so this is in quadrant 1. Okay, quadrant 1, you expect both x and y to be positive, and in fact x is positive and y is positive, and so this is a good check, okay, to make sure that the answer worked out. All right, so let me look if there's any questions in the chat here. Guys look all right. Okay, let's do number 2. So in number 2, I have r is 3.5 and theta is 225. 225 is quadrant 3. Why? Because it's bigger than 180 but less than 270. All right, the formulas are the same. Okay, nothing mysterious. Okay, like that. And if you just plug in the numbers, let me do that. You get this answer here, and you get that answer there. Okay, so I hope I'm not going too fast. I'm just cutting and pasting because I don't want to waste your time, punching away at my calculator here. But I'll just go over it slowly. So I have x is equal to r cosine theta. R is 3.5. Theta is 225 degrees, like that. And if I work that out, I get negative 2.47. There are more decimals, but like in this course, I'm just rounding off always to 3 significant figures. Same thing for y. It's 3.5 times the sine this time, sine of 255. And that's going to give me actually the exact same number. Okay. And is it in quadrant 3? Yes, because in quadrant 3, you expect both x and y to be negative, and they are. Okay. Now, I want to start showing you some patterns in sines and cosines. Here you notice that both the x and y values are exactly the same value. And you go, well, why did that happen? I mean, it's got something to do with the angle, but why is that the case? And so here's a little pattern that you should see with sines and cosines, okay? Cosine of 0 degrees is 1, okay? So that's something you can memorize. Cosine of 90 degrees is 0, like that, okay? Sine of 0 degrees is 0, and sine of 90 degrees is 1, like that, okay? And what you notice is that the cosine starts at 1, and as you go up to 90, it decreases to 0. Conversely, the sine starts at 0, and as you go up to 90 degrees, it goes up to 1. So they go in the opposite direction. They're actually equal to one another at 45 degrees. So cosine of 45 degrees is equal to the sine of 45 degrees, and they're both equal to 0.707, like that, okay? And there's some more decimals there, but again, I'm just rounding off, okay? And at this point, you go, well, what's that got to do with 225? Well, it's this. Anytime you have an angle which is a multiple of 90 degrees, the sine and the cosine are either going to be 0 or 1 or negative 1, okay? So, you know, like if you have cosine of 0, you've got 1. If you have cosine of 90 degrees, it's 0. If you have cosine of 180, it's actually negative 1. So whenever you're at a multiple of 90 degrees, you're going to be either at 1 or 0 or with a sign there, like possible plus or minus sign. If, however, you're at a multiple of 90 degrees, plus 25, you always get this number here, which is actually equal to 1 over the square root of 2, okay? So it's actually equal to 1 divided by the square root of 2. Not that you have to memorize that, but, you know, just to tell you. And so if you have like 225 degrees like that, okay, that could be written as 180 degrees plus 45 degrees, like that. And of course, 80 degrees is just 2 times 90. Okay, so you can see there's the multiple of 90 plus 45 degrees. So whenever you have an angle which is a multiple of 90 plus 45 degrees, the sine and the cosine are going to be identical, and it's going to equal this number here with a possible plus or minus in front. Okay, so just a pattern that you should see when you do these problems. And the reason I mention these patterns is you don't need them because of course you've got a calculator in front of you, but the more patterns you see in the sines and cosines, the better intuition you have into how sines and cosines work. And if you do make a mistake on your calculator, you'll see it right away. So for instance, you know, here it's 225. You should go, oh, that sounds like it's one of these multiple of 90 degrees plus 45. So the two numbers had better be the same, except maybe a sign in there, like a plus or minus sign. And if they turned out to be different, like if this one turned out to be 3, like that, then you would know that you did something wrong. Okay, so, you know, it's just a way of kind of correcting any possible errors. All right, and so, well, there's question B. Okay, and question C. This is really simple. Again, it's again a polar to Cartesian, so I'll just cut and paste that answer there, like this. All right, and I guess we should say what quadrant it's in. It's in quadrant 4, like that. It's in quadrant 4, and we have that x is equal to r cosine theta, like that. So that's going to equal 1.3 times the cosine of 337, like that. And crunching that through my calculator, I got 1.20, okay? And then the other one was y is r sine theta. Crunching that through, I got negative 0.51, okay? And now, if you look at the two numbers, you see that x is positive, y is negative, okay? And that's in quadrant 4, all right? So let me do this one maybe on the other whiteboard just so you could see it. So remember, x is positive, y is negative. So over here, you're in the situation where, let's do it in purple, x is positive, so you're over here on this side of the y-axis, and y was negative, so you're down here, and so you're in quadrant 4. Okay? So there you go. That checks out. Okay, the x and y values and the angle is in quadrant 4. I didn't say that, but it's kind of obvious. That angle is greater than 270, less than 360, and that's quadrant 4. Okay. All right. So now um, this one I give you x and y. Okay. And that means I give you the Cartesian and I want you to calculate the polar. So for polar, there's r and theta. The r part is the easy part. It's the theta part that's tricky, okay? And actually it's for the theta part that you need the quadrant. So if you take a look at this, x negative, y positive, that's quadrant 2, okay? So to get r, it actually turns out to be just the Pythagorean theorem, like that, okay? So I'll show you why in a minute. Okay, I'll go to the other whiteboard and I'll show you why it turns out to be the Pythagorean theorem. But let's finish the problem first. Okay, so r is basically equal to the square root, and I can't do the square root like in this text editor. I can't do the square root sign, so I'm just going to write sqrt. So it's the square root of x squared plus y squared, like that. Okay, and now when I solve this, copy paste. Like that. When I solve this, I have to be careful here because I'm going to put x there and I'm going to put y there, and I'm going to have that value in there and that value in there. I have to be careful because when you square that negative 3.4, make sure that you square the negative along with the 3.4. Okay, so I mean, you guys probably know this, but since we're going over it, it's probably worth pointing out the kind of common mistakes I've seen students do on their calculator. If you type negative and then you type 3.4 and then you square the 3.4, what happens on some calculators is that it'll only square the 3.4, okay, and it'll give you that value, and then it'll carry the negative sign in front, and that's wrong because you squared the 3.4. It's like you did this. It's like you squared the 3.4, but you left the negative sign out in front, and that's not correct. You are squaring the entire number, including the negative sign, okay? Now, you should know that when you square a negative number, that's just a positive number. So actually, whether there's a negative sign there or not doesn't make any difference, okay? But I just want to make sure that you know that if you just type in your calculator negative 3.4 squared, some calculators will square the 3.4 and they'll carry that negative in front, giving you a negative number for this entire piece here, and that's incorrect, okay? And you'll get the wrong answer. So yeah, if you type negative 3.4, make sure it's all squared, okay? Or for this part, for r, you know what? You don't even have to write in that negative. Just square 3.4 because negative 3.4 squared or 3.4 squared, it's the exact same value. Okay, square 1.4, add them together, take the square root, and the answer turns out to be 3.68. Okay, so there we go. So let me know if I'm going too fast. I mean, on the one hand, I don't want to waste your time. But on the other hand, I don't want to go so fast that you can't be taking notes, okay? It's hard for me to tell in this environment if I'm going too fast or not. So don't be afraid, you know, to slow me down. Okay, so there you go. And I'll show you why the Pythagorean theorem is required there. The next one is theta. And here's why theta is tricky. Because the most important part of the formula is this part, the inverse tangent part. So it's the inverse tangent. That tan to the exponent -1 is the inverse tangent. That's the most important part, or inverse tangent of y over x is the most important part. But you have to add, if you're in quadrant 2 or 3, excuse me, if you're in quadrant 2 or 3, you have to add 180 degrees, okay? And I'm going to try to show you why that's the case with my last two problems, actually, all right? So the way this works, and I went over that in the pre-recorded lecture, there's the inverse tangent of y over x. But then if you're in quadrant 1, you don't add anything. If you're in quadrant 2 or 3, you add 180. And if you're in quadrant 4, you add 360. And that might seem strange to you. You go, well, why isn't just the tangent, the inverse tangent, why isn't that enough? Why do you have to make this extra rule in there? And it has to do with the fact that the inverse tangent is a multi-branched function, okay? And that means that your calculator only knows about one branch, but you know, depending on what quadrant you're in, you might be on a slightly different, not a slightly, but you might be on a different branch of the function, and you have to compensate for that by adding in 0 if you're in quadrant 1, or 180 if you're in quadrant 2 or 3, or 360 if you're in quadrant 4. Okay, and again, it might seem mysterious, but like these last two questions here, I'm going to try to show you exactly why you have to have that 180 in there. Okay, but for now, let's just make sure that we can work through it. You have to know how to do inverse tangent on your calculator. Okay, and be careful that's not take the tangent and then the reciprocal of it. It's like on some calculators, it's like a button, like you have to press this button called inverse and then tangent, like that. It's actually a function all of its own. It undoes whatever the tangent function does. So it's the opposite of the tangent function. Okay, so there's the formula, and here we have to substitute in for y, and we have to substitute in for x, and the sign is critical here. So y is 1.4. So for y, we'll put in 1.4 there like that. And for x, it's negative 3.4 like that. Okay. And so we get the inverse tangent of 1.4 divided by negative 3.4. Okay. And just crunching that through my calculator, I got the following. I got, well, I don't know why I rewrote all of that, but there you go. I got 158 degrees. Okay. It turns out that when you do the inverse function, the argument here is negative. It turns out to be a negative number, and so that's why you get a number less than 180 degrees. Okay. Quadrant 2, you expect your answer to be between 90 and 180, and it's 158. Okay. So there we go. All right. Let me take a look here in the chat. Okay, let's do the next one. Next one for R, it's the same formula. Okay, and we're substituting in for x and y next. All right, like that. Whoops, I got a. Okay, so there's 1.7, so it's 1.7 squared. There's negative 2.2, there's negative 2.2 squared. The negative being squared along with the 2.2, and you should get an answer of 2.78. Okay, now what quadrant is this in? So this one is x is positive, y is negative. That is quadrant 4. Okay, like that. And in quadrant 4, it's this formula right here, but in quadrant 4, you have to add 360 degrees. Okay? All right, so substituting in, I get the following. All right, so in quadrant 4, I guess I could just say right here, quadrant 4. In quadrant 4, it's the inverse tangent of y divided by x plus 360 degrees. Okay? And so you do the inverse tangent of, the y value is negative 2.2, don't lose the negative sign there, divided by 1.7, the x value is 1.7. Okay, so divide those out, then take the inverse tangent of that, add 360, and you get 308 degrees. Okay, and is that in quadrant 4? Uh-oh. I had a temporary disconnection. It's reconnected again. So if you saw a little bit of a blip there, let me know in the chat if something went wrong. I mean, I got an indicator here that for about 10 seconds or so I was disconnected. A little buggy, but you're good. Okay, thank you very much for that feedback. Yeah, I mean, like I've got a lot of indicators that tell me about the health, and so yeah, it was just a little bit of lag, but we seem to be good right now. Let me just take a look. Excellent connection. So, okay, let's go on. All right, so this next one is meant to try to show you why you need that the 360, and I'll do that on the other whiteboard. But there's also the Pythagorean theorem, so I'll do both of those together in a minute. But let's take a look at this question first, and let's solve it. So if you take a look here, I have x equals 2.1 and y equals 1.7. This one is in quadrant 1 like that. Okay, and then I also have here x is equal to negative 2.1 and y is equal to negative 1.7. So both of the x values have the same absolute value, the same magnitude, 2.1, but in the first one, x is positive, and in the second one, x is negative. And same thing for the y values. Okay, so it's the same absolute value, 1.7, but for the first one, y is positive, and the other one is negative, like that. Okay, so this one is in quadrant 3. All right. Well, let's solve for r. Let's do them both at the same time. Let's solve for r for the first one, and r for the first one is r is equal to the square root of x squared plus y squared. Okay, and that's equal to the square root of 2.1 squared plus 1.7 squared. And if you work that out, that turns out to be 2.7. If you do this for the second one, you get the same answer, because it doesn't matter that it's negative 2.1 and negative 1.7, because when you square negative 2.1, the negative goes away, and that's the same as squaring 2.1. And when you square negative 1.7, that's the same as 1.7, and so you get the same answer both ways. So both of these vectors, even though they're in different quadrants, they're the exact same length. They're the exact same size, okay? They're both 2.7, I guess, meters, or whatever the units are here, okay? Let's do the angle, all right? And the angle for this one is going to be the inverse tangent of y over x. And because we're in quadrant 1, we don't add anything. So you could think of it as add 0 degrees, but adding 0 degrees is nothing. Okay, so you have the inverse tangent of y over x, and if you substitute in the numbers, you're going to get inverse tangent of 1.7 divided by 2.1. Okay, and that's going to give you 39 degrees. Okay, so there's the angle for the first one, and it is in quadrant 1. You expect the angle to be between 0 degrees and 90 degrees, and it is. Okay, so that's working out. Let's do it for the next one. Okay, so for this one, it's this formula here, but now you're in quadrant 3, and in quadrant 3 you're supposed to add 180 degrees. Okay, but let's do this carefully. Watch what happens to just this part of it. Okay, so yeah, the 180 is there, but let's put it to the side for a second. Okay, and now let's substitute in the numbers that we have. Okay, so there it is. Okay, for y I'm going to substitute in negative 1.7, and for x I'm going to substitute in negative 2.1, like that. Okay, and now you'll notice that you have a negative number in the denominator here, and a negative, sorry, in the numerator, and a negative number in the denominator. But when you have a negative divided by a negative, the negatives cancel. Okay, and so what I could do on the next line is I can just take out the negative signs there, like that. Okay, and now you'll notice that this value right here, inverse tangent of 1.7 divided by 2.1, is exactly the same as in the previous question. Okay, so if you were to crunch this through your calculator, what you would get here for this piece there is that 39 degrees. Okay, if you had forgotten that 180 there, you would have gotten that theta is 39 degrees, which is in quadrant 1, not in quadrant 3. Okay, so these two vectors, this one here and this one here, they're actually off by 180 degrees. And you're going, well, why didn't the tangent function by itself not see that? And it's because you have this ratio y divided by x. Okay, so if y is negative and x is negative, that formula is not going to be able to tell the difference between that situation and where y is positive and x is positive. So if x and y are both negative, or x and y are both positive, you get the same answer out of that formula. And so it can't tell the difference, just this piece of it can't tell the difference between quadrant 1 and quadrant 3. Okay, as a result, you have to manually say, oh, no, I know these negatives are going to cancel, but I'm in quadrant 3, so I got to bring in that 180 degrees there, like that. Okay, so that's what's going on there. All right, last thing that I'll do, so that solves that problem. Last thing that I'll do is I want to show you why Pythagorean theorem comes out. I know that I did that in the pre-recorded lecture, but now that you've seen it here, let's see how that works out. So let me switch back to my whiteboard there, like that, and let's look at that triangle. Okay, and I'll actually etch it out in red And my diagram's getting a little bit messy, but let me make this base of the triangle here. Okay, extra thick red. And that, of course, that's x. Okay, then the height y is along here, but you could also just make this height here y. Okay, and this is a right angle triangle with two sides x and y, and the hypotenuse is r. Okay, so you have a hypotenuse r of a right angle triangle with x and y, sides x and y, and Pythagorean theorem says that r squared is going to equal x squared plus y squared. Okay, there you go. There is the Pythagorean theorem coming out of that triangle. So that's how you relate x and y to r. And of course, we don't want r squared, we want r, so we just take the square root of both sides, and that's why to calculate the r from x and y, you just use r is equal to the square root of x squared plus y squared. Okay, so these are pretty easy questions. Let me see if you have any questions in the chat. All right, I'm not seeing any new questions, but let me go on then to the next question. If you still have some questions, and I'll see them later, I'll come back to them. Let me go on to the last question here. So this last question is incomplete because you haven't seen how to solve 2D kinematic problems yet. Okay, it's just how you set them up, and basically I want to show you how to begin drawing that diagram, and I'll do a much better job next week, but I want to show you why the initial position, we'll do at least the initial position. I don't know if we have to do the initial velocity, but I'm going to show you why the initial position has to be two numbers. Okay, so again, why did we do all these vectors? In 2D, a vector is always two numbers, and that's because the initial, the position, the velocity, and the acceleration, whether it's initial or final or whatever, those three quantities have to be vectors. They have to be expressed in terms of two numbers. So I'm going to show you how to get that initial position, identify that initial position, and it'll turn out to be two numbers. Okay, so I have here a cannon, which is placed at the top of a hill, which is 45 meters high. Okay, and I'm going to fire a shot which with a velocity of 350 meters per second at an angle of 35 degrees above the horizon. Now, if that language is a little bit confusing, I'll show you what that means as I draw the diagram, okay? And I'm asking you to place the origin at ground level directly below the cannon. Okay, again, I'll draw what that looks like, and I want the initial velocity, initial position, initial velocity, and acceleration. I think it's sufficient just to show you the initial position. Actually, now that I think about this, because again, the point of this is to show you why these things must be vectors. Okay, so let me switch again to my other whiteboard here, like that, and let me start with a fresh image, and let me zoom in like that. Okay. Great. So now I said that I have a cannon placed on the top of a hill. So step number one is to just physically draw what you would see. Okay. And I'm going to do that in black. So here we are at the top of a hill here like this. And the hill goes down like that. All right. And the hill is 45 meters high, but I'm not even going to draw that in here. Okay. And at the top here, I have a cannon. And so I'm going to do the best I can to draw my cannon. That's the wheel, and this is the cannon itself, okay? And I'm going to fire a shot. So here we go. Here's the shot. It goes up and travels, and it comes down along a parabolic path like that. Okay? So there you go. That's what you would physically see. Let me just extend this a little bit here like that, the ground like that, okay? And that's what you would physically see. So that's your first step, is just like to draw a picture that physically represents the physical situation. The second thing, and I'll draw this in blue, is to put your coordinate system down, okay? And that means in 1D it was just x, but in 2D that means x and y. And there's also time in there too, okay? Although we don't need time right now, okay? And so I'm going to put the x-axis along the ground level here like that. So here's my x-axis. All right, positive x. All right, and I asked you to put the origin. So the cannon originally is, I guess, somewhere in the cannonball. The shot is somewhere inside the cannon. So I'm going to put the origin directly below that, and that would be right here. So there's my origin. Okay, and you say, well, is that good enough? can I do this as a 1D problem? Well, no way, because see the black path there, that's the path that the cannonball takes, and it's a curved path. Okay, and so that's just not, you can't say where it is. Like, it's not like that the cannon's somewhere along the blue line at all times. It's going along this curved path, and that curved path is in a plane, and so there's no way to avoid doing 2D here. Like, for instance, I mean, the cannon is balls right there, but at some point it's going to be there. And I say, where is that in the plane? And as soon as I say, where is it in the plane, you're going to need X and Y, okay? And so this has to be a two-dimensional problem. So we're going to have to put the Y-axis like that. And of course, the Y-axis goes through that origin like that. So here's plus Y. All right. And it goes through the origin there. And now I say, what is the initial position? Well, the initial position is right there. That's where it is physically. But I can't just use one number. Like in 1D, I would have said the initial position is x naught, like that. Okay? And you say, well, okay, what's x naught? Well, x naught is just, it's actually 0, because along the x-axis, the cannonball initially is, if its x projection is right at the origin. But that doesn't tell you how high it is. So you're actually going to need the height as well, which is your y. So these two numbers together will describe where the cannonball is, okay? And so in this picture, it's at x equals 0, because it's right on the y-axis. And at y is equal to, I said the hill was 45 meters high, so at y is equal to 45, okay? Like that. So that's where it is there. If I asked where is it there, okay, I mean, I'd have to give you more information. But, again, you couldn't just do it with the x value. The x value is just there, okay? So if I just gave you the x value of that point, all right, you would say, well, it's traveled from the origin. It's traveled from the origin to that point there. But you wouldn't know how high it is, okay? Or if I give you the height, like off of the y-axis there, you wouldn't know how far along x it's traveled. So everywhere along that trajectory, you need two numbers. You need x and y to describe where the cannon shot is. Okay, and so there's the story with x. Okay, with position. What about velocity? Let me do that in red. Well, I won't actually work out the velocity, because you'll see how that's done in the video that you'll watch next week. But the velocity is somewhat in that direction there, like that. It's actually 30 degrees above the horizon. Okay, so it's like that. But you can see here that even that vector there is a vector in an xy plane, and so even for the velocity, it's an initial velocity, but you're going to need an x component for the initial velocity, and you're going to need a y component of the initial velocity, okay? And then the acceleration, that one's a little easier because it's straight down, okay? It does have an x component and a y component, but the x component is 0 because it's straight down. If the acceleration were, like, I don't know, to the right here, like that, it had, like, it was downwards but a little bit to the right, then it would have a little bit of an x component. Or if it were the other way, like that, then it would have a negative x component, okay? But it's straight down, and so the x component of the acceleration is 0. The y component, of course, is negative 10 meters per second squared, okay? And that's the story with the acceleration, and it doesn't change over time because it's always constant acceleration downwards, okay? But you could see that whether you're talking about the position, whether you're talking about the velocity, or you're talking about the acceleration, you always have to have two numbers, okay? Because it's because they're vectors in a plane, all right? The only one where you don't need to have two numbers is the time. Okay, because time is still a scalar. Scalar just means a single number. Okay, so t, because it's at t equals 0, it's there, and I don't know because I didn't work this problem out, but it might be at t equals 10 seconds, it would be there. Okay, it's not like there's a tx and a ty. All right, there's just like one time. All right, and so that's a scalar quantity. All right, so I mean, I know I didn't answer that question or didn't go much further, but I just wanted to give you the fundamental principles and why you needed vectors to do this. And the last thing I'll say, and then we're done, is here you can see that I was working in Cartesian because at every point I was always talking in terms of x and y. But if you read the problem, I actually say, for instance, for the velocity, I say that the velocity is 350 meters per second at 30 degrees. And as soon as you hear the word degrees, that's polar. So in my word problems, I might give you polar information, okay? But in the equations that you're going to use, you're going to have to convert to Cartesian because the equations that I give you are only in terms of the Cartesian. So if the word problem gives you the information in polar, you're going to take that information and convert it to Cartesian. Okay, so that's it for for this lecture. A little bit short, but that's because this was a shorter week, so I gave you a little less work because of because of Labor Day on Monday. Well, let me ask you guys if you have any questions. If not, then we could just end the stream at this point. Okay, so because of the little bit of a delay, I'll just wait and see if you have any questions. I'll also ask in the chat. Any questions? Or are we good to end the live stream? Okay, we're good. I got one response, so I'll wait just a little bit longer. I assume if people aren't responding, that's because you've fallen asleep at the keyboard. But all right, we'll end it off at this point.